We're in your packet on page 24. We're on lesson 9 and we're looking at tangents to a circle. So hopefully you've already filled in the toolkit for this. This is just a little bit of a review of what was on the toolkit for this lesson. So a tangent line intersects a circle at exactly one point, and we call that point the point of tangency. So in this diagram here, AB would be the tangent line, and then A would be our point of tangency. Okay. So a line is tangent to a circle if and only if it is perpendicular to a radius drawn to the point of tangency. And we'll say radius, but technically this segment could also be a diameter if it went all the way across to the other edge of the circle. So radius, or I'll put in parentheses here, diameter would also work. So what we're going to do, I'm going to do the left column with you on this page 24, and then you're going to be doing all of the even questions on your own. And feel free to come to some live classes or come to office hours if you have more questions. So first thing we want to do in this question here, or in both of these two questions, we're looking to know if the line segment AB is tangent. So if this is a tangent segment, that would mean there would have to be a right angle symbol here. And in order for there to be a right angle, this would have to be a right triangle. So if we have three segment lengths in a right triangle, we have the 8, the 15, and the 17. We want to know, will those segments actually fit into Pythagorean theorem? Remember, a squared plus b squared equals c squared. So if these numbers 8, 15, and 17 fit into that Pythagorean theorem, then this creates a right triangle. So looking here, this would be the hypothetical place of our right angle. So these would be our legs. So we want to know, is 8 squared plus 15 squared equal to 17 squared? So if it is equal, this will be a tangent line because it's a right triangle. And if it's not equal, then it won't be a tangent line. So 8 squared, that's 64. 15 squared, that's 225. And 17 squared, that's 289. So on the left side, if I combine the 64 and 225, that would be 289. So I get 289 equals 289. So what that tells me is that, okay, these numbers fit into the Pythagorean theorem, therefore it creates a right triangle, and therefore I have a right angle symbol here. So yes, this is a tangent. So yes, AB is tangent to circle P. So you're going to do the same thing in this problem here. The only thing I want you to keep in mind is that 5 is just for this little section here. So you're also going to want to draw in this length here. We have a radius of 11. This radius would also be 11. So then you're going to want to take that into consideration when you figure out the length of this whole entire segment here. Okay. For the next questions, we are assuming that it's tangent. So we know it's a right triangle. I'm going to put my right angle symbol here. And then based on that knowledge, we are solving for our variable. So these two sides here would be the legs of the right triangle. So 7 squared plus 19 squared is equal to x squared. So 7 squared, that's 49. I don't have 19 squared memorized. That's 361 is equal to x squared. Let's add those two together. That's 410 is equal to x squared. And the only way to undo something that is squared is with a square root. So I'm just going to take the square root of 410. That's in simplest radical form, but our approximation for that will be about 20.248, And 248 would remain 248. So we'll say x equals square root 410, which is approximately 20.248. I usually round to 3 decimal places. You're going to do the same thing in this next question as well. But keep in mind, again, similar to this problem right above, this length here is actually also part of the circle. This is the radius. So this is 11. This segment here would also be 11. So keep that in mind before setting up your Pythagorean theorem question. The next set of questions here, remember in our toolkit, we just discovered that if two lines are tangent to a circle and they meet at the same point, they're going to be equal. So we'll just pull out the toolkit here. We were just looking on page 21. And that's because we technically can create, if we draw on a radius, two triangles that are congruent to each other, and those parts would be congruent as well. So essentially, we know that these two pieces here are equal, so we're just going to set them equal. So 5x plus 23 equals 8x minus 19. Okay, so let's bring all of our x's to one side. We can subtract a 5x on both sides. That gives us 23 equals 3x minus 19. And we can add 19 to both sides. And x, if we divide by 3 on both sides now, x should be 14. And you should be able to do the same thing with this question here. On this question, it actually even kind of shows you the diagram of what we create two triangles. So remember, these would be equal here. We know these are tangents, so there's right angles. They both share this common side, so therefore these sides have to be congruent as well if the triangles are congruent. So you're just setting these equal here. And then on our last question, we have a bunch of different pieces that are considered tangent to the circle. So what I mean by that, these segments here are tangent to the circle and they both meet at Q. So those two little pieces that I highlighted in purple are going to be equal to each other. Let me grab another few highlighter colors. I like to color code things. These pieces here meet at the same outside point, so they're going to be congruent to each other. These two pieces here would also be congruent to each other. And then our final two pieces here, they would also be congruent. So we'll actually start there. So these pieces here, because if we created a kite or if we created two sets of congruent triangles, they would be equal. I put 23 here. Well, this also is going to be 23 then. So they're congruent. Now, we know that this entire length of this side is 37.5. And if I take 37.5 and I subtract 23, what I'm going to be left with is this part here, which is 14.5. 23 plus 14.5 gives us that whole segment length. So that means this part also is going to be 14.5. Okay, I'm just kind of still going around the circle. So we've got this part here. Okay, we've got this part good. So that means this other orange piece is 27.1. And then to figure out the last pink piece, because I want the perimeter of the entire shape, I'm going to take 52.5 and I'm going to subtract that 27.1. And then this pink piece here is going to be 25.4, which therefore means this pink piece is also going to be 25.4. So if I'm looking for the perimeter of this shape, I'm just adding up all the sides together. So I have the length of this whole side. I could split it up into the two parts if I wanted, but I have 37.5. That's this side here. That's what we'll start with. This side, we'll just add those two pieces, 14.5, 27.1. So that's this whole side. This entire side, we already have the whole thing, so we can put 52.5. And then our last side over here is in two different parts as 23 and 25.4. So if you want, you can just add all the little individual pieces, but I just did these two as their own entire side lengths. And now we're just adding up all the entire segment pieces there. So 37.5 plus 14.5 plus 27.1 plus 52.5 plus 23 plus 25.4. And so that means our entire perimeter for the shape is 180. And we don't have units, so I just put units. It's not squared because it's not the area, so that's our perimeter, so P for perimeter. And it has nothing to do with degrees of the shape, so keep that in mind. Okay, now for this shape here, you're finding perimeter of triangle. So it might be helpful if you wanted to highlight some pieces to see, which parts would be considered equal to each other. And then we have, the last pieces here. And then you're just finding the perimeter of the entire shape.